Hi, I'm Ben-Yaakov. This presentation is entitled Testing the Transient Response of PWM Converters by LTspice. There are two videos relevant to this presentation. Here are the videos, these are the links, and I'm going to print the links in the description section of the video that you are now watching. I highly recommend to watch first this video, the first one, especially since it lays the foundation of the subject matter we're discussing here. Now, there is a disclaimer here that the controllers shown in this presentation are for educational purposes only. There is no recommendation or endorsement implied. Other manufacturers offer similar devices. We are talking about PWM converters working in closed loop. So basically, we have a closed loop system, which the generic form seems something like that. We have an error amplifier, which senses the output, and then we have a modulator, power stage, which feeds the output. Now, we are concerned in this presentation about the response to a step. Now, the step could be at the reference, could be at the input, or could be a load step of current that loads the output. And the question is, what is affecting this response? And this is the subject matter of this presentation. Now, a feedback system, and I'm showing here like a generic representation of a PWM converter. Here we have the phase compensator, we have here the power stage, and this is the voltage divider. Now, here's the reference, this is summing point, and since this is a closed loop system, negative feedback, we know that this is the relationship for the transfer function between the reference and the output. Now, this gain here, starting here, going all the way around, is the loop gain. Okay, so this is the loop gain. And when the loop gain is larger than 1, the 1 drops, and then the response is really independent on the system itself, on the loop gain itself. It is a function in this particular case of 1 over k, which means that the output is following the reference within the voltage divider. However, what happens if the loop gain is not much larger than 1? So we are at this point, this is now the loop gain in the body plot, and here is the cross section, and this is the 0 dB, and here we have the phase margin. The phase margin is actually the measure how close are we to 180 degree, which means now positive feedback, in fact. And we know that the phase margin is affecting the response of the closed loop. In fact, overshoot, oscillation, etc., stability really depend on the phase margin. We'd like it to be like 45 degrees or larger. And we're talking about phases after actually subtracting the 180 degree of the system itself. That is here, this is already built in, so this is why it is plus, otherwise it should have been minus. So this area here is really responsible for the dynamic response of the system in closed loop, and we are talking about a linear system. As discussed in the video that I've referenced, we can relate this phase margin to the behavior of the system. It turns out that if we have a phase margin of, say, 45 or smaller than that, then the system behaves as a second order system, and then we have a quality factor, which is a function actually of the phase margin. The phase margin is a function of this distance here, and then the quality factor is a function of the phase margin, therefore. So when the phase margin is small, the quality factor is high, and then we're going to have an overshoot in the time domain, and then we're going to have a peaking in the frequency domain. This is the basics, of course, of the behavior of a second order system. It turns out that when the phase margin again is small, the system behaves like a second order system. So I'm going to examine by simulation two systems to demonstrate this issue of the crossover. I have here one case in which I have two poles, and this is like a network like this. And then I have here another case in which I have a second order system, and then by a 0 I have here a crossover again of 20 dB per decade, which means that the phase margin could be reasonable. And this is the relevant network. And in the case of a PWM, this would mean that we either have a resistor here, which causes the zero, or perhaps a type 3 compensator, which introduces a zero. So I'm going to examine these two by simulation. And here is the first circuit. What I have here, this is the section now. This is like the system itself. And here's the error amplifier. And then I have here a buffer, which has the capability of clamping. It is important. We'll talk about it later on. But now this is not functional, so I'm going to run it without any clamping at all. And then I have the second case of an LC circuit in which I have here a resistor to get a good phase margin. And again, I have here the error amplifier of the buffer. And in both cases, I've added this source, which is an AC source, the purpose of which is to get the loop gain in the frequency domain. And you can do it because when you run an AC analysis, then you might say that you have an input here going all the way and then it coming back here. So the ratio between this voltage and this voltage is in fact the loop gain. So this can be done very conveniently with LTspice. So here are actually the loop gain of the two cases. Now we see here the second order behavior of the LC. We see here the two poles of the RC circuit, but I've adjusted it such that the crossover at 0 dB is the same frequency for both with the same phase, meaning the same phase margin. And here are the two cases, one on top of the other. You see that it's pretty close here, and the phases are pretty close here. And in fact, it's zooming in. I've done some trial and error process. Eventually, I gave up. And this is what I came up with. For the RC, the crossover is 13 kilohertz, phase margin 52. Here it's 11 kilohertz and 45 degrees, which is pretty good. So the two systems are pretty much the same in terms of the crossover. And here are the responses, pretty much the same. So, of course, there is some difference. And again, the phase margin of the LC circuit is somewhat smaller, so therefore you expect a much higher. But you might say that the behavior is really very similar. And also, if you look at the frequency of oscillation, then there is a factor of 2. But again, it's reasonable, and that's pretty good as far as we are concerned here, the first order, just for demonstration. But if we look at the input voltage at the system, and I'm talking about the voltage here and the voltage here, we find that in this linear system, the voltage is here 1 kilovolt and here about 300 kilovolt. Meaning that in order to get this nice response, the system has to generate a very high input voltage, especially for the LC, of course, because there is an inductor. And if you'd like to get a fast response at the output, a fast rise time, then you need a very high voltage. And this is what the system is actually doing. Here it is. Now, obviously, this is not realistic for a practical system. In real system, the voltage here, like in a buck converter, is limited to the supply voltage. So it cannot go higher than that. So now I'm invoking the clamping. I'm not allowing this circuit to go much higher. So this is for the LC case, and this is for the RC case. You see that in the LC case, there is some oscillation, and also here we have a different response. Here is a close-up. This is for the LC, just the startup. You see that the voltage goes all the way to 10 volt and clamped there. And the voltage starts to go very slowly. Meanwhile, it oscillates. And here, the RC, again, it's clamped to 10 volt, which is limiting the rate of rise here of the output voltage. So we see that limitation, in this case of a voltage, a clamping of a voltage, is really changing the behavior. And this is in fact what we call a slew rate. That is, a nonlinear behavior causes a given slew rate to the system, which is not related to the equations that we have seen before of a second order system. It has nothing to do with it. I mean, it's affected by it, but it's not following the equation that I've shown earlier. So the interim conclusion is that slew rate is a nonlinear phenomena. It's a manifestation of a current or voltage clamping within the circuit, and it is not a consequence of the expected linear response. So the question is, given that, how do commercial PWM controller fare? And I'm going to now examine a number of controllers to see how they behave when exposed to a step, just to see if there is any relationship to the closed loop response as predicted for a linear system. So the first case is LTC3703 controller, and this is a demo circuit given by Analog Devices. And we have the controller. We have also outside transistors, and here is the LC. This is a buck converter. Now I've added here a source, a sinusoidal source. This is like a poor boy network analyzer, and the idea is that if I'll find a frequency at which the voltage here is equal to the voltage here, meaning that as you go from here all the way, coming back, and you come to here, and the voltage here is the same amplitude than here, this is the crossover frequency, because you have a gain of 1. So here are the two signals, the small signal that I'm injecting here, like 10 millivolt. I'm showing the voltage here and the voltage here, and I can also approximately estimate the phase margin. Well, it's not very accurate, but just a ballpark of it. So what I find is for this system, the crossover frequency is 20 kilohertz. The phase margin is about 47 degrees. And this converter is running at a switching frequency of about 300 kilohertz. So this is the first case. So now I'm exposing this system to a step. Now I cannot go into the reference, of course. So what I'm doing, I'm injecting here a current into this junction, which of course goes into the feedback into this amplifier here, error amplifier. And I have two sources. That is, I have a one which is injecting a positive current, meaning the voltage will go up, so therefore the output will go down. And then we have the other polarity too. So this is just to see the response, you might say, to a reference. And here is what I see. This is just the startup of the converter, okay? And here we have the two cases, the one injection, one direction, another injection, the other direction. This is the inductor current, and this is the midpoint. So what we see here is, as I inject a positive current into the junction and the voltage has to go down, we see a very slow slope here. And this is because the current goes to 0, meaning that actually the half bridge is turned off, the two transistors are turned off, and in fact this drop is due to the discharge of the capacitor via the load. Here it is. This is the capacitor, which is fairly large, by the way, and this is the load. So what we see here, this is just discharging, and this is what is causing this change here. Nothing to do with the response of a second order system, okay? And then I have the other way around, and then I have a very sharp rise of the current, which then is tapering off, and since it is going down, then the rate here is changing. Again, this is not exactly what is expected. Now, the rise time here is about 380 microseconds. Now, if this would have been a first order system, we know there is a relationship between the bandwidth and the rise time, 0.35 over the bandwidth. And this is 17 microseconds. Now, a second order system should be, in fact, faster than that. So this would be for first order, And second order will be like, I don't know, 5 or something like that, and I get 380. So you see that the response here is really limited by some other circuitry within the unit, and it's not a second order type of a response. Also, we see here that this is certainly non-linear because the switching is turned off, and again, the two transistors are off. Now, this is for a large signal. It's supposed to cause a 5-volt drop. So let's see what happens with a small signal. Okay, so I have here only a drop of 0.1, that is, I've reduced the injection to be very, very low, and the drop is only 0.1. Again, you see that the response is very slow. It's the same order of magnitude I've seen before. So you see that for a step in the reference, the response is not really described by the second order behavior. Now I'm doing a load step, and this is by having two current sources of 3 amp. One is injecting current here, and one is actually causing the current to increase. Both are 3 amp. And now this capacitor is very large, 270 times 2, it's a 540 microfarad capacitor. It has a built-in, doesn't show here, of 30 milliohm each one, so the ESR, the total one, is 15 milliohm. Now we know that when you have a load step of a current, then the first thing will happen is to have a jump or a spike due to the current passing through the ESR. Now, having an ESR of 15 milliohm and a current of 3 amp, you'd expect something like 45 millivolt spike, independent of the question of second order or anything like that, okay? So this is be a major response in this system when you load it like that. And here it is. What we see, this is the output now. This is, again, the inductor current. And here we see that this is about 60 millivolts. That's about the order of magnitude that we're talking about here. It's also about 50 millivolts. So in fact, what we see, the major behavior of this response is due to the ESR. And here I'm showing it in a close-up. We see that the capacitor voltage is going down. The inductor current is rising relatively slow because there is a limited voltage here, and then it goes up. At this point, the inductor current is about the same as the load, okay, but the voltage is low, so therefore there is a need for more current, and the current is increasing. This is now the nominal current, and it is now increasing, and then it's oscillating. So you see that this major part here is the slew rate effect, has nothing to do with the second order behavior. Now I am examining another controller, LTC3810. This is a P current mode with a constant on time. So it's another method. I think it's a newer controller anyhow. And in this case, doing the same Pooh-Boy testing of a network analyzer, I find that the crossover frequency is 27 and the phase margin is 56. And the switching frequency is about 30 kilohertz now. Since it is a constant on time, during transient, the frequency might change. But on the average, we have a switching frequency which is similar to the one which we just discussed for the voltage mode converter. The phase margin here is 56 degrees and the crossover frequency 27. So we can say that the two systems have just about the same crossover and just about the same phase margin. Now, if we have a current mode, then we have an extra loop here, which is in fact reducing the order of the system. Because now the inductor becomes like a current source, and when you have a current source going into this RC circuit, it's a first order system. Obviously, this is correct only when you are within the frequency of this loop. So now I'm exposing the system to the same injection, and here it's first of all at the reference, or the feedback you might say, with the two current sources. And now I'm comparing the two, the current mode with the voltage mode. So this is the current mode, a small signal. You see the behavior here. And here is the current mode, large signal. This is also the large signal. And this is the large signal zoomed into this point. Now, interesting, in this particular case, you see that during the drop here, the drop of the voltage at the injection, the voltage at the midpoint is zero, meaning that the lower transistor is on, okay? And since it is on, there is a process of discharging the capacitor via the inductor, and you see that the negative current of the inductor goes to a very large value. And this is because the inductor is discharging the capacitor very quickly. See it here. Okay. So now comparing the two, we see the following. You see the drop here. You see the drop here. This is about the same scale. Okay. And here there's no current, and here is a lot of current for discharging the capacitor. At the on time, okay, and they increase the rise time here, we see that the current of the voltage mode is sort of tapering off, and therefore it's slowing down the rise, while you see here that in the current mode, the current remains high. So this voltage now jumps fairly fast. So you compare the two, you see quite a bit of a difference, although in general, they have the same switching frequency, the same crossover frequency about the same phase margin. So you see that current mode is indeed superior, no question about that, in the transient, and it really has little to do with the second order response. I mean, most of the response is due to nonlinear behavior. Now I'm going to do an injection at the output, just a load step, and again I'm comparing the two. So this is the current mode, and this is the voltage mode. Now, as far as the inductor current goes, we see here a fast drop and a fast rise, while here there is a slower drop plus some oscillation, and also we have it here. This is the voltage mode. But when I compare the peaks here and here for the two injections that is loading this positive current and negative current, you see that the magnitude is not much different. In fact, in the current mode, a little bit higher than that. So, and this is because the peak is primarily due to the ESR, which has nothing to do with, again, the current mode, the voltage mode. This is just the nonlinear behavior of the system. Now I'm going to do some experiment to see the effect of phase margin. So I'm taking this voltage mode controller, and here I'm showing the error amplifier, and this is a type 3 compensator, or PID. You see this network at the input, and you see the network at the feedback. So it is compensating the second order behavior of the LC. This is the voltage mode. And I am now corrupting the phase margin by changing this capacitor from 2.2 nanofarad to 500 picofarad, okay? And checking now again with this poor boy approach, I find that indeed the phase margin is very small, very difficult to estimate it. They're just about one on top of the other, so maybe it's like 10 degrees or 15 degrees, while in the original design it's 56 degrees. Here it's very small. And also the crossover now frequency is 11 kilohertz, while it was 27 kilohertz. So it's a bit different. And now I'm comparing the two cases, the original design with a phase margin of 56 and the case of the small phase margin. You don't see major differences, although we see a somewhat different behavior at the drop here. In fact, the rise time here is faster. This is actually expected because if you have oscillation, then it should go up faster than without oscillation. Here we see also that the inductor current is sort of clamped to a high current, while here it's tapering off. So this explains this fast response here as compared to the response here, which with a tapering inductor current. So we don't see a major difference. Well, there is some oscillations here and some oscillation here, but it's not oscillating. But you see that it is on the verge perhaps of instability. And now, when I'm comparing the load step, again, the peak values are not much different than earlier, but for the case of the small phase margin, we certainly see here oscillation. So you can see that indeed with the phase margin, the peak itself is not really related to the second order behavior. It's more like the ESR, but then the oscillation afterward are certainly related to the quality factor of the system. And here, of course, with a small phase margin, the Q is high, and this is why we see this oscillation. Now, what are the conclusions here? Now, theoretically, closed-loop PWM converters have a second-order response, and the theoretical response depends primarily on the phase margin. A slew rate is a nonlinear phenomena, a manifestation of a current or a voltage clamping within the circuit. Like in the case of operational amplifier, we know that the slew rate is due to a limitation of the current or current sources within the amplifier. Now, due to the slew rate, the practical system rarely behaves as a linear second-order system, only part of the time. Now, during the slew rate duration, the system is really operating in open loop, and then voltage mode control may induce oscillation following a step, and then current mode control reduces the oscillation and may shorten the rise time. And finally, load step response is primarily affected by the output capacitor, or I should say the ESR of the output. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it'll be useful to you in the future. Thank you very much.